So this question is asking us to determine which vibrational modes of a water molecule are spectroscopically active. Yeah. So right here we have our water molecule H2O, and we need a couple things to determine this. First, we need our irreducible representation, which has already been determined and is listed right here. And then we need our character table, again from Appendix C in the textbook. And we know it's this CNV group character table because our C2V is our point group. So the first thing we want to do is determine the number of vibrational modes we should expect. And this can be done using the formula 3n minus 6, with n being the number of atoms in the molecule. Now, because we have an H2O molecule, we know there are 1, 2, 3 atoms, so 3 times 3 is 9, minus 6 equals 3 vibrational modes expected. The next thing we want to do is determine which of our characters are going to be translations and which are going to be rotations in order to determine the final vibrations. So translations can be determined by looking at the character table and seeing linear functions of x, y, or z. So when we look here, we see A1 has z, which means it's a translation. B1 has x, meaning translation, and B2 has y, meaning a translation. On the other hand, rotations are denoted in the character table as linear functions Rx, Ry, or Rz, and we see that A2 is a rotation, B1 is a rotation, and B2 is a rotation. Now, it's important to note that B1 and B2 can both be seen to have translations and rotations, and this is important for later. So, we list our translations as A1 plus B1 plus B2, and our rotations as A2 plus B1 plus B2. In order to find our vibrations, we need to take our irreducible representations, which are right here, and from that we need to subtract our translations and our rotations. And once we go through and do that, we are left with 2A1 plus B1 as our vibrational modes. And this lines up with our expected value of 3 vibrational modes. So one thing to consider is symmetry aspects, and for both of our A1 molecule or A1 modes, we know that they are symmetric, and one will represent a stretch while the other represents a bend. And these are symmetric because they don't change the symmetry of the molecule. On the other hand, our B1 mode does change the symmetry of the molecule, making it antisymmetric. And it represents a stretch. So we know that IR active modes are IR active if they change the dipole moment and match linear functions x, y, or z. So we do know that each of these change the polarizability, which indicates IR active, and we can look at the table and see that they do match. A1 and B1 do match Z and X, making them IR active. Then we do know that vibrations can be both IR active and Raman active if they match the functions for both. So next we want to look at our Raman active. And modes are Raman active if they change the polarizability, which is the ease of electrons to be distorted from their initial position, and if they match xy, yz, xz, x squared, y squared, or z squared functions. In our table, looking again at A1 and B1, we see that, we do in fact have a match from x squared, y squared, z squared, and xz does match, indicating that both are Raman active. So this means that all 3 of our vibrational modes are going to be both IR active and Raman active.